Hello, and welcome to the University of Liverpool's STEM Outreach A-Level Teaching Resources for Particle and Nuclear Physics. Today we're going to look at the constituents of the atom. In 1897, Joseph J. Thomson developed the plum pudding model of the atom, which visualizes the atom as a sphere of positive charge with negative charges distributed throughout, like fruit in a sponge pudding. Ernest Rutherford was a graduate student of Thomson, along with Niels Bohr, who went on to propose that electrons orbit the nucleus later. And they investigated the structure of the atom with the Rutherford Scattering experiment. The experiment conducted between 1908 and 1913 involved firing alpha particles, which are helium nuclei produced in radioactive alpha decay and have a positive charge, at a thin sheet of gold foil. A fluorescent screen was placed all around the experiment, which would give out a flash of light when it encountered an alpha particle. Rutherford's graduate students, Hans Geiger and Ernest Marsden, conducted this experiment and were able to calculate the angles that the alpha particles had been deflected as they passed through the gold atoms in the foil. The results were not consistent with the plum pudding model. Many of the alpha particles passed straight through the gold atoms, but some were deflected, with few of these at an angle greater than 90 degrees, which could only be explained by an electrostatic repulsion of two positive charges, the alpha particle and the nucleus. The results led to the development of the Rutherford model of the atom, which is mostly empty space in an indefinable sphere of negative charge with a dense, positively charged nucleus at the centre. Rutherford won the Nobel Prize for his discovery in 1917. Rutherford's new atomic model developed further into the modern nuclear atomic model, particularly following James Chadwick's discovery of the neutron in 1932. Thanks to the work of physicists like Thomson, Rutherford, Bohr and Chadwick, we now have an understanding of the structure of the atom. The atom is made from a dense nucleus containing protons and neutrons, which is orbited by electrons. Let's take a look at the particles that make up the atom in more detail. It's important to note the difference between relative charge and actual charge on each particle. If we look at the proton, the relative charge of +1 translates to an actual charge in coulombs of 1.6 times 10 to the power of -19. Its relative mass of 1 converts to an actual mass in kilograms of 1.673 times 10 to the power of -27. For a neutron, it has no charge, and its mass of 1 actually converts to a relative mass that is slightly different than that of the proton of 1.675 times 10 to the power of -27. The electron has the opposite charge to the proton. However, its mass is much, much less by an order of thousands. Again, the positron has the opposite charge to an electron, but has the same mass. Let's look at mass and atomic numbers A and Z. You can find the information about each atom of each element from the periodic table. The numbers in the top and bottom right of the element tell us how many particles are within the atom. The mass or nucleon number A is the total number of nucleons, which is the number of protons plus the number of neutrons. The atomic number Z is simply the number of protons. This number is what makes an atom a specific element and is also equal to the number of electrons in a neutral atom, making the net charge of the atom 0, as the negative charge of the electrons cancels the positive charge of the protons. Let's take a look at an example. Here is an atom of lithium with a mass number of 7 and an atomic number of 3. We know the number of protons is 3. And we can work out the number of neutrons by subtracting this from the nucleon number. The number of electrons will be equal to the number of protons, as this is a neutral atom. Please note, particles do not just drop out of an atom like this. This is simply to help us visualize the numbers. It's important to consider the specific charge on particles and nuclei. Specific charge is defined as the charge per unit mass of a particle, atomic nuclei, atom, or ion. This is measured in coulombs per kilogram. If we look at the charge for the proton and the mass of the proton, the ratio between these two gives us the specific charge of plus 9.564 times 10 to the power of 7. The neutron has no charge and therefore has no specific charge. The electron has the inverse charge to the proton, however, its mass is much less. So there is much more charge distributed throughout its mass. If we look at the example of the lithium atom and work out the specific charge of its nucleus, we must consider the charge of all of the protons. So multiply the proton charge by 3 and add this to the charge of any other nucleons in the nucleus. The neutron has no charge, so this doesn't factor in. We now add the masses together, where we multiply the mass of the proton by 3 and add this to the mass of the neutrons, which now does factor in. There are 4 neutrons, so multiply that by the mass of the neutron, and add it all together, we get the full mass of the whole nucleus. If we now divide this total charge by this total mass, we find the specific charge of this specific nucleus. Whilst the atomic number makes the atom a specific element, the mass number can vary, making a number of different versions of the atom called isotopes. Here we can see the simplest atom, hydrogen, containing just 1 proton and 1 electron. An isotope of hydrogen, known as deuterium, contains 1 neutron also. Tritium is another isotope of hydrogen and contains 2 neutrons. These isotopes are involved in the steps of stellar nuclear fusion and go on to form new elements later. Similar to hydrogen, carbon has isotopes carbon-13 and carbon-14, with the latter being radioactive. This means that it will decay via a beta-minus decay to nitrogen-14, as the beta-minus decay involves a neutron transforming into a proton, changing the atomic number, and therefore changing the atom into a new element. We can use this for an incredibly useful purpose. The isotopic data we use in carbon dating enables us to find out how long something has been dead. Living organisms continually absorb and contain carbon in their bodies. Plants through photosynthesis, where they absorb carbon dioxide and convert this into sugars. Animals then consume the plants, and the carbon is passed through the food chain. The Earth's atmosphere has a specific percentage of carbon, and this itself is made from different percentages of the carbon isotopes. Carbon is oxidized into carbon dioxide, which is absorbed by living organisms only when they're alive. When the organism dies, it stops taking on any more carbon, and the percentages of the carbon isotopes in their bodies will be the same as the distribution in the atmosphere initially, but the radioactive carbon-14 decays over time, and this distribution changes. Using what we know about the radioactive half-life of carbon-14, which is about 5,000 years, and testing how much is left in the body, we can calculate the amount of time the organism has been dead. Please take a look at our other resources. For teachers, on tes.com, search for UOL Physics, and for students and teachers, they can visit our STEM outreach website. Please like and subscribe to our YouTube channel to receive updates about new resources and content.